So now in topic 2.2 we're going to look at accelerated motion, and this accelerated motion essentially refers to any kind of change of velocity, but the technical definition of it is the rate of change of velocity, and by rate of change of velocity I mean specifically the change of velocity with respect to time. That's a vector quantity, and we can define it through a formula, small a, which is the symbol for acceleration, is equal to the change in velocity over the change in time, and we also might break that change in velocity down, so oftentimes we'll drop the vector symbols and we'll just simply use the labels, and we'll say that v minus v naught divided by the time change. So v minus v naught represents the change in velocity, divide that by the amount of time that it took to make that change in velocity, and you get the acceleration. Much like velocity, it's a vector quantity. That means that it has both direction and magnitude. An important thing to notice, there's actually two types of acceleration, and the two types of acceleration are a result of the vector property of the vector quality of velocity. That is to say that velocity has both magnitude and direction. If either of those change, then you will experience acceleration. For the purposes of this topic, we're going to focus entirely on the magnitude, and then in a subsequent topic we'll look at the aspect of changing the direction of that and the sort of special type of acceleration that leads to. Just as we saw with the velocity formula, this formula is for the average acceleration. If, however, we want to turn that into instantaneous properties, and the purpose for turning it into instantaneous acceleration would be to be able to calculate the final velocity, the initial velocity, the time, or obviously even the acceleration. And in order to be able to make that sort of calculation and find useful information from that, we need the instantaneous acceleration. Well, just like with the velocity, there's sort of two ways. One is by looking at the velocity change over an infinitesimally small time interval. This won't provide the instantaneous acceleration, but it is an approximation of the instantaneous acceleration. And if we make the time change very, very small, then that means that we'll be getting very, very close to the instantaneous value of the acceleration, and therefore, even though it's an approximation, it's a good approximation. It basically gives us the value of the acceleration. An even better way to do it, though, is to not have the acceleration change. If we maintain a constant acceleration throughout the entire motion, then constant acceleration will turn this formula for average acceleration into the formula for instantaneous acceleration. And then it becomes much more useful because we can calculate or solve for any one of the four properties. Really important to notice that there are four variables, and any one of those can be solved for. It's not just a formula for acceleration, in other words. It's a formula for acceleration, a formula for velocity, a formula for initial velocity, or a formula for time, depending on which of the four variables that we're looking for. So as a result of that, let's take a look at this equation and look at it in a form that is almost even more common than the definition. So we'll start with v minus v naught over t, and what I want to do is to solve for v, the final velocity. Oftentimes during accelerated motion we would like to know, based on the initial velocity and the time in the acceleration, what will be our velocity at the end of the motion. So let me just make a couple of steps. I'm going to multiply by t to give me at is equal to v minus v naught. I'll add the v naught to the other side to get at plus v naught. And so this is a very useful version of the form. This is a little weird way of looking at it, though, so let me go ahead and put it in our final form. If you look closely at the formula, you can see that there are essentially two variables, because remember, this is a situation in which we're going to use this equation for constant or uniform acceleration. That means the a in v equals at plus v naught is a constant, an unchanging property. Also, once the motion starts, obviously the initial velocity will not change. That now also becomes a fixed quantity. So with this being a fixed quantity and that being a fixed quantity, I hope that you recognize that this is the equation of a line. The variable that I would plot on the vertical axis would be the velocity, and I would plot that versus the time, and what I would find is for a constant or uniform acceleration, this thing is going to produce a line. So let me make a note of that. This is the equation of a line. And let me just remind you, the equation of a line is y equals mx plus b. Okay, so let's just take a look at one quick example, and then we'll move on to some variations of the acceleration equations. So in our first example, we're going to take a look at Sarah, who's jogging at 2.5 meters per second. When she begins to accelerate at 1.5 meters per second squared, so it's important to notice the units for acceleration. If we slide back down here, I'm going to get a change in velocity. Well, the change in velocity is meters per second. When I divide meters per second by seconds, then I end up with meters per second squared. And she's going to accelerate at that rate of 1.5 meters per second squared for 4 seconds. And the obvious question then is, what is her final velocity? Just like with any problem, the most important thing is to pull out what is given to you, so we can take it from being a word problem to being more of an algebra problem. So I'm just going to go in order of the things that were given to me. First I was given V naught, and that was a positive 2.5 meters per second. I was given the acceleration, 1.5 meters per second squared, and I was given the time, that was 4.0 seconds. And I'm looking for the final velocity. I would expect when I look at your solutions to problems that, particularly now as we're getting to more complicated problems, that I'm going to see this list of given information. The next step is I'm going to see the equation that you're going to use to solve this. In this case, the equation is very easy because it's already solved for the variable that I'm looking for. If, however, it was not solved for the variable that I was looking for, what I would expect from you is to solve for the variable first, then go and plug in your given information, and go ahead and then go to the calculator and plug things in. But in this case, it's already done for us. So we're going to plug in the acceleration of 1.5 times 4.0, and we'll add that to the original 2.5 that we started with. So in this case, 1.5 times 4.0 will give me 6.0 plus the original 2.5. So what essentially multiplying a times t is going to give me is it's going to tell me how much the velocity increased by. Every 1 second of motion, I will increase my speed by 1.5 meters per second. For every second that I move, or Sarah moves I should say, the velocity will increase by 1.5 meters per second. So for 4 seconds, that will give me 6 meters per second increase, and my final answer then, since she was already moving at 2.5, then I'll end up with 8.5 meters per second, and that's my final answer.